So these are the contexts of statistical distributions in our world. And so now let's go back to the name of this class. Let's talk about R and how we deal with these in R. So in R, every statistical distribution, or almost all of them, come attached with 4 different types of functions. They're kind of general classes of functions. The first one is a class of functions that starts with the letter R, and R here stands for random sampling. And what this is going to do is to randomly output values from the distribution. It's going to take a fake sample for you and tell you what numbers it saw. And we usually use this to make fake data. There's a lot of situations where we're trying to kind of figure out a method or figure out a plot or figure out what's going to happen. And we want to generate some pretend data in order to illustrate that concept. You'll see this in the lab. So here's an example. I always read this as run if, but that's not what it is. Now it's stuck in your head and I'm sorry, but this is R unif. Generate a random sample from a uniform distribution. And I said, please give me 3 values, and here are my 3 values in this particular random sample. If you try this code and run it, you'll get a different 3 values. It's randomized every time. And you'll notice here that I said a uniform random variable is in a range, right? We're equally likely to get every value in a certain range. But I didn't specify a range here. I don't have to. There's a default range that happens to be 0 to 1. You could find this in the documentation for the RUnif function. It would tell you those optional arguments and what their default values are. But here, if I want to change them, I can say, actually, I want a range of 10 to 20. And here we go, there's 3 values in that range, randomly selected. And similarly, maybe I want 3 normal random variable values. For those that are familiar, the normal distribution needs to know the mean, the center, and the standard deviation, how fat is that bell curve. And so there are default values. Again, there's 0 and 1. But of course, we can specify our own. We can sample from a very different shape of that bell curve and get very different values. And so hopefully you're getting the picture by now. For the t distribution, we have R and then t, random sample from the t distribution. You have to give the t distribution a degrees of freedom. If you don't know what that is, go take more statistics. It's not our concern in this class. And with the binomial distribution, we need to tell it how many tries we had and what the probability of success. So think of it as how many coins did we flip and what are the chances of getting heads. And so in our first trial, we got 5 heads out of 10, second trial 7, third trial also 7. And lastly, the chi-square. Again, not going to come up too much this week, but I want you to see it and know that it exists. So those are the R functions. The next class of functions is the P functions, and P stands for probability. And the idea here is we want to compute the chances of getting an observation that falls under a certain value. By convention, we're always giving R the top cutoff, and it will tell us the probability of landing below that. And we usually use this for p-values. Hopefully in a previous class you've come across p-values. If you haven't, that's okay. We'll touch upon them in a couple weeks. But this is sort of for asking the question, how likely is a certain outcome to happen? And so here I'm saying, what is the probability of a normal distribution sampling one value and getting a number less than 1.5? And this is for a standard normal, again, for those default values of a mean of 0, a standard deviation of 1. And we see that 93% of the time, you would expect your value that you sample to be smaller than 1.5. Or we can look at this in the height context. We can say people's heights have an average of 5'7", a standard deviation of 3 inches. That's about how far people tend to be away from 5'7". And so then we can ask the question, what are the chances of a person being taller than 5'10"? And we could see here, being shorter, my mistake, is always below. These p functions is always the area or the probability below. So we have an 84 chance of seeing the next person walk by and they happen to be shorter than 5'10". And then if we wanted to know how likely they are to be taller than 5'10", we say, well, if they're not shorter, then they're taller. So 1 minus, or 100% minus 84%, we have about a 16% chance of seeing someone taller than 5'10" walk by outside the window. So let's do a little practice here. I've been talking for a while. I want you to try to answer these questions using the functions that you've just learned. What is the probability that a chi-square distribution with 35 degrees of freedom gives a value of 25 or less? You may not totally know what those mean, but see if you can match those pieces to the function. And what is the probability that 10 coin tosses of a fair coin give 6 or more heads? Take a second, try these. Don't sink too much time into it, but please do type into your R console and try these things out. All right, let's look at the answers. So for the chi-square distribution, we said, all right, I want a probability from a chi-square distribution. The value that I'm interested in is 25. I want to find the probability of being below 25. So that's my first argument, is the value I'm interested in. And then we also need this kind of peripheral information to help define the shape of that distribution. And that's where the degrees of freedom kicks in. So we have about a 10.5% chance of this happening. Not very meaningful in the real world, but good practice. More meaningful in the real world, we might say, what's the probability that 10 coin tosses give 6 or more heads? So the value we're interested in here is 6, but hopefully you see why I didn't put 6 in the first argument. So the size and probability, those are pretty straightforward. A fair coin is 50-50, and we have 10 tries. But I realized that p binom gives me the area below. So if I had just done p binom 6, etc., I would be getting the probability of 6, 5, 4, 3, 2, 1, or 0 heads. That's not what I want. I want 6, 7, 8, 9, 10 heads. So what I'm going to do, since I know that p binom gives me below, is I'm going to say, what's 5, 4, 3, 2, 1, 0? And then give me everything else. And so I found the chances of 5 or fewer heads, and then I flipped it, and I said, oh look, about a 38% chance of 6 or more heads. Okay. Moving swiftly along, the next class of functions is the Q functions. This stands for quantile. This one's a little hard to wrap your head around. This one says, you give to me a probability. I'll give you back the value that has that probability below it. So I'll give you back the value such that the chances of the random variable sampling a value that small are whatever probability you gave the function. It's kind of weird. I think of them as the backwards version of the p functions. We don't use them that often. There are contexts that you might need them if you become a statistician, but I don't find myself using these very often. But you should be aware of them, so let's just show how to read these. So Q norm of 0.95. That says what value of a normal distribution you have a 95% chance of getting that value or less. And that turns out to be 1.64. You only have a 5% chance of getting something bigger than 1.64 if you sample from a standard normal. Or if you want to think of it in real world context, 95% of people are shorter than what? That's what I'm asking here. I'm saying a mean of 5'7", standard deviation of 3 inches. 95% of people are shorter than what? And R says, about 72 inches. About, 6 feet tall. So let's try this quickly before we lose our little headspace. So if I randomly sample a number between 16 and 22, I'm 80% sure that number will be smaller than what? And for those of you who remember your statistics a little better, what is the critical value for a one-sided t-test at the 0.05 significance level with a sample size of 50? All right, let's take a look. If I uniformly sample between 16 and 22, notice I changed that word, it's a hint for you there. I want to know the quantile, in fact the 80% quantile, from the uniform distribution between 16 and 22. See how I translated that sentence into code? And what I get back is 20.8. Be careful, this is not 20.8%. This is saying 20.8 is the value that we are 80% sure that we are going to get less than. And for this one-sided test at the 0.05 significance level, we would say, okay, what value has 5% of the area below it, or potentially above it? And we get about 1.68. So that's our critical value. Lastly, we have, of these four functions, we've gotten through R, P, and Q, and now we have D. And D stands for density, which is the height of that distribution curve. If I showed you those plots again, it would be the height of those blue lines. Now for discrete distributions, like the binomial, this tells us the probability of getting an exact value. It says, how likely are we for this very specific single outcome to happen? For continuous distributions, this is kind of meaningless. I can't really ask the question, what are the chances that the next person is exactly 5'9"? Because how do I know they're not 5'9" and a quarter, or 5'9" and an eighth, or 5'9" and 1/100th, or 1/1000th? You just can't get perfect precision, right? Any height is technically possible. And so with continuous distributions, the density is not really a meaningful measurement. So we really only use this in the context of probability for discrete distributions. So try this out, the chances of exactly 12 heads and 20 coin tosses, and now we've got an unfair coin that tends to land tails a little more often. Give it a try. All right, I hope that was straightforward. I hope this is getting a little smoother for you. Here's the answer. We would like the density, the exact height of the distribution for the binomial at the value of 12. For this situation where there's 20 tries, and be careful there, did you catch that one? I asked about 12 heads, but I said there's a 70% chance of tails. So make sure that you're translating these into their true real-world meaning, and not just putting the numbers in the function in the order that you see them. And we see here that this is highly unlikely. For this unfair of a coin, we probably won't get 12 heads.